Hello everyone, welcome back to ArcGIS channel. In this video tutorial, we would like to learn how to conduct various spatial point pattern analysis in ArcGIS Pro environment. We will reconstruct one of the history's most iconic map, John Snow's 1854 Colorado map that his work laid the foundation for modern epidemiology. Using maps, he identified the sources of a deadly cholera outbreak in London, which was the Broad Street pump. So in this lab, we will reconstruct the John Snow map and we will use modern spatial point pattern analysis to examine the evidence. So let's get started. So the very first thing you have to do is that create a new folder, 8 point pattern, and then copy and paste the point pattern zip file and then expand it or extract it because ArcGIS cannot read the zip file. So in this folder, we have 3 sets of data. The first one is the location of deaths. This is at the household level. It's a CSV file. We also have the location of pumps in London, and it's also a CSV file. And also we have a georeferenced map of the London for the year 1854. And this is georeference, means that you can measure the distance, you can measure the area on this map. So it's in the real world coordinate system. I'm going to open up ArcGIS and create a new project. So point pattern, and save it in lab 8 folder, and OK. So let's add the CSV file map, add data, and here is the location of pumps.csv. OK. So if you open up the attribute table of this pumps, so we have 8 pump in London. So we have the name of the pump, which is actually the name of the streets that their pump located. And also we have the address, latitude and longitude of the pump. So since it's latitude and longitude, so it's in the geographic coordinate system, right? And also WGS84 is the datum or is the ellipsoid that has been used. So we're going to use this information, WGS84, for mapping these points, to convert the CSV file to point on the map. So the next one is location of deaths. As I mentioned, this is at the household level. So if you open up the attribute table, so there are 369 households, the information that we have, with at least 1 death. So, but in some households, as you can see, death count. In some households, we have more than 1 death, right? So if you want to see the minimum, maximum, the average, and the total number of deaths, so you have to easily right-click on that field and explore statistics. And here you can see, for example, the minimum is 1, the maximum is 18, and the average is almost 2, and also the total number of deaths, sum is 706. So let me close this, close CSV and close pump. So the next data that we need to add is the map of London in 1854 that has been georeferenced. As I mentioned, it means that the coordinates are in the real world coordinate system. So if you click on add data and then a snow map and then OK. So here is the map of London in 1854. First of all, let's look at the coordinate system of this data. If you right click on this map, properties, source and spatial reference. So first of all, it's in the projected coordinate system. Why? Because it's based on the meter. As you can see, the values are very large, right? It's a projected coordinate system, so you are able to measure the distance or area on this. You don't need to convert it to the projected coordinate system. And these are the information for the ellipsoid or spheroid that they have used, major axis, minor axis, flattening factor, and so on. So click OK. I'm going to compare this map, which is for 1854, with the real map, which is here. You can also use the OpenStreetMap if you want, but I think topographic map is also okay. When you, let's say I'm here if I select the snow map, you can see another tab will be added right here, raster layer. Select the raster layer, and here you can increase the transparency. So you can make this layer transparent. So for example, I want to set the transparency to 50%. So what happens is that you can kind of see the previous map as well. So you can kind of compare these two maps, right? So for example, you can see there are some buildings that don't show here, right? So, or like for example, in some areas there were some small changes, but in general, the location, the roads, the streets are almost the same. I am going to convert this CSV file to point on the map. So when you have the coordinates, and also when if you know the coordinate system, you can easily convert them to geographic information or points, right? So if you right click on pumps.csv and then create points from table, XY table to point. So here we can say that my input table is pump. I'm going to the output, because it creates a feature class. So the output, I'm gonna save it in GIS lab 8 folder. I'm gonna call this pumps. So it's a shape file, as you can see, .shp. So the X field is longitude, so automatically identified is longitude. The Y field is latitude. The corresponding of X is longitude. The corresponding of the Y is latitude. And also the geographic coordinate system, also it automatically identified that based on the numbers GCS and WGS84, which is correct. So if you want, you can change it. We can click on here and then select another coordinate system, but it's true. And based on the data that I have, and then click OK. So what happens is that here are the location of the pumps. You can compare it with reality. So you can label it, for example. So Broad Street, and here also you can see it's Broad Street, right? So these are the location of the pumps. I can make it much nicer. So for example, I can select this one and use probably a blue one right there. So these are the location of pumps in London. So let me remove the labels. So let's also repeat this for deaths. I'm going to convert the CSV file to points on the map. So create points from table, XY table to point. So for death, create a new shape file, GIS labs, and I'm gonna call this death. So X is longitude, Y is latitude, geographic coordinate system is correct, and then OK. So as you can see, it converts this to point and also adds a new feature class or shape file to the table of contents. So also you can change the color, for example, to red. So these are the location of this. I'm going to show the pumps on top of this, so I can move it here. All right, so from this map, it is hard to say, to analyze this point pattern, right? So the very first thing that I'm gonna do, I'm going to create a proportional map of the deaths based on the death count, right? So if you right click on the death and then symbology and then select proportional symbol, not based on ID, based on death count. So here we can see, for example, most of the deaths are clustered or deaths with the higher number. So let me move it on top of the pumps. So these are the deaths with the higher number, are more clustered around the Broad Street pump, right? This pump, right? But it still is not easy to identify the pattern yet. So we need to use spatial point pattern analysis. Sometimes in other projects, it's very hard to distinguish a pattern from the data. So we need to use the spatial point pattern analysis to statistically evaluate the pattern, okay? So the very first technique that I'm gonna use is called mean center. And mean center is what is the center of all of these deaths, right? If I take an average for X coordinate, if I take an average of Y coordinate, so where is the center of the deaths, right? So, and also you can weight it based on the number of the deaths, right? So we can have a weighted average, weighted mean. So how this works, so here based on Esri, so for finding the mean center, just add the coordinates up, divided by sample size or the number of deaths, and also add the coordinates for y component, add them up divided by sample size. So you will have the mean center. So you may also say that in some households we had multiple deaths, right? So in that case, in order to account for that, you can calculate the weighted mean center. So WI here is going to be the death count, right? So how we can apply that in ArcGIS? So it's very simple. You have to go to Analysis tab, Tools, and then Toolboxes, and select Spatial Statistics, and then select Measuring Geographic Distribution, and here is Mean Center. So identifies the geographic center for a set of features. Where is the concentration of the data? Where is the center of gravity of the data? So the input feature class, so I'm going to find the center of gravity for death, right? So it's going to be death. And also the output is going to be death mean center. So this is okay in the lab 8 folder. So weight field is going to be death count, right? Case field is used when you want to group your results. Okay, so let's say you have a field based on the region A, B, C, D, and you want to find the mean center for each of these regions, right? So in that case, you have to use case field to identify the mean center for each of these. But I want to just find a single mean center for the entire data set, so I do not use the case field. Okay, so as it also explains that if you want to have a separate mean center based on the case field, but I don't want that, so run. All right, so here is the mean center, and as you can see, mean center is very close to the Broad Street pump, right? So if I want to measure the distance, if I go to the map and then measure based on probably, like, let's say based on feet, so it's very close from here to here is almost 100 feet. So as you can see, the center of the data, the average or the center of gravity of all of the deaths is very close to the Broad Street pump. So that's the first evidence that this pump maybe is the source of the pollution. So you may say that, okay, so here maybe we have some outlier extreme values. How about instead of mean center, I calculate the median center? Let's also calculate the median center. So median center, it's when you want to your analysis not to be influenced by extremely high or extremely low values in terms of the coordinates. So again, if you go to Analysis tab here, median center, select the median center, and then for death, the death median center, the weight field is going to be death count, and then run. So the median center is also very close to the mean center, so which means that we don't have any much outlier in the data set, right? The definition says that the median center minimizes the overall Euclidean distance to all of the features in the data set. Okay, so the next analysis is standard deviational ellipse. So what is the standard deviational ellipse? So according to the Esri, directional distribution or standard deviational ellipse. So first of all, it creates and summarizes the central tendency, dispersion, and direction. Okay, so I can identify the direction, I can summarize all of the data or most of the data with just one ellipse, right? So the calculation is kind of complicated, as you can see, for calculating the direction of the ellipse and calculating the dispersion of the ellipse. So you can feel free to study that. But the most important thing for this ellipse is that, so according to the rule of thumb, so we have one standard deviation ellipse, two standard, or three standard deviation of the ellipse. So if you have a one standard deviation ellipse, 68% of the data will be within this one standard deviation of ellipse. Two standard deviation of ellipse, almost 95% of data fall into this two standard deviation ellipse, and 99.7% of the data will fall within the three standard deviation of ellipse. And this is for if your distribution is a normal distribution. in general, is if you have one standard ellipse, one standard deviational ellipse, it has 63% of the data, two standard has 98% of the data, and three standard has almost all of the data will be in this ellipse. So if you go to Analysis tab, Tools, and here directional distribution is standard deviation ellipse. So my data is going to be the DES information, and here DES directional distribution is fine in the lab 8 folder. And so you can set the ellipse size. You can have, for example, one standard deviation, which, as we saw, it has almost 68% of the data if the distribution is normal. If it's above 63% of the data. And weight field is going to be the DES count, right? And then case field no, and then run. So what happens is that it created an ellipse like this. So this ellipse has almost 68% of the data is within this ellipse. So you can have two standard deviation ellipse. So let's create a three standard deviation ellipse. So this is going to be almost all of the data. Okay, so for this, so this is going to be 3. So I'm going to call this 3. So this is 3 standard deviation ellipse. So, and also I can call this area of interest. Okay, because it's almost 100% of the data. So I'm going to call this AOI, or area of interest, and 3 standard ellipse. Weight field is going to be DES count, and then run. So here is our 3 standard ellipse. So I don't need it right now, but so remember that this is AOI is 3 standard deviation ellipse. So I'm going to uncheck this. So I'm going to put it here, but I am going to make it better. Okay, so for example, I'm going to change the color green, and I can increase the transparency, or maybe another color. Almost 68% of the data. And also look at the direction of this ellipse. It's almost in the direction of the broad street. That is another evidence that, as you can see, so if I put this pump on top of the others, and as you can see, almost 68% of the data or of the DES are clustered around these pumps that is in the broad street pump, right? So the center of the ellipse is actually the mean center. So here was the mean center. So that's the center of the ellipse. So the next analysis that I'm going to perform is Thiessen polygon. So what is the Thiessen polygon? So according to the ArcGIS, so if you have a sets of points, right? So like this. So Thiessen polygon are some polygons that, first of all, they are unique. So that any points that are, for example, in this polygon are closer to this point. For example, this point is not close to this one or this one, right? This point is definitely close to this point. So for each point here, it creates an area of influence. So where is my area of influence? Where is the area that all of the data that are within that area are closer to me? So that's the Thiessen polygon. So how can I use this Thiessen polygon ArcGIS, and then how can I interpret that in terms of the John Snow map? So I'm going to create the Thiessen polygon for the pumps. So I want to see the area of influence for the pumps, right? So I am going to, first of all, for the DES, I'm going to use a single color here, and maybe red. Probably I don't need to show this, and also the mean center here. So I'm going to create, again, the Thiessen polygon. So from Analysis tab, Tools, and then if you type Thiessen, so create Thiessen polygon. So your input feature is going to be the pumps. So I'm going to see the area of influence for the pumps, right? So pumps create Thiessen polygon, or pumps underscore Thiessen, right? So here it says that the output field for the Thiessen polygon, do you want to have the information from your input data, which is pump, or not? So you can also have all of that, or doesn't matter, this is not important, so I click run. And again, I select this Thiessen polygon and then go to the feature layer, and I'm gonna set the transparency to 50%. So what you can conclude from this map? So from this map, it created a Thiessen polygon. I can say any point that is in this map is closer to this pump, right? So you can see only 2 points, right? So here more, but here look at the Broad Street pump. So look at the area of influence of the Broad Street pump. So most of the deaths are closer to the Broad Street pump, right? As you can see here. You can also count number of the deaths that are closer to the Broad Street pump. So this is going to be based on the number of the households actually, right? So how can I do that from Broad Street pump? If you open up the attribute table, so here was the Broad Street pump, right? This one. Okay, so I can count the number of the deaths that are within this selected polygon. Again, this is selection by location, right? So if you go to the map, selection by location, I want to select the deaths that are completely within this selected feature, which is the pumps Thiessen, right? Which is just one record, and apply and OK. So these are the deaths that are closer to the Broad Street pump based on the Thiessen polygon. So how many deaths are closer to this? So if you right click on deaths, open up the attribute table. So 178 deaths out of 369, which if you do the calculation, so 178 divided by 369, so almost 50%, 48% of the deaths according to the Thiessen polygon are closer pump to the Broad Street pump. But this was based on the number of the deaths based on the number of houses, but I want to see the total number of deaths, right? So if I click on here and then explore statistics, here shows me the total is 392. So 392 deaths. So what was the total number of the deaths? If I think here 392, right? So if I right click here, so 392, I think it was 700 something. If I 392 divided by 706, so almost 55% of the total number of deaths per case. So it's not going to be based on per household. So over 50% of the deaths are closer to the Broad Street pump. So another thing that we can investigate, if you remember in the previous labs, we talked about global clustering, right? For aerial data. So we use Moran's eye, we use general G to examine if the distribution is clustered, random, or dispersed, right? But we talked about that for the aerial data, but how about for the point data, okay? So for the point data, we use another analysis. So there are a variety of analysis that you can have for the point data, but the simplest one is if you go to the tools tab and then I think analyzing pattern, average nearest neighbor. Okay, so what is average nearest neighbor? How it works? So let's say, so for all of the points that I have, for example, for this point, what is the nearest neighbor? So this one. So calculate the distance. What is the nearest neighbor for this one? Calculate this. So if I repeat this and calculate the distance for the nearest distance for all of the points, right? And then take an average of that. So that is going to be the observed nearest distance, right? Observed average nearest distance. So if I take an average, so if I calculate that for each feature, calculate the nearest distance, add them up, repeat this for all of that, add them up divided by sample size. So that's the observed nearest distance, right? And also, if we assume that the distribution was random with the same sample size, with the same number of the observations of the deaths, So we can find the expected average nearest distance, right? So if you divide the observed divided by the expected value, so that is going to be ANN, or average nearest distance, okay? So it is obvious that if observed is less than expected, which means that the distances are closer to each other compared to the expected, which means that the value of the ANN is less than 1, so this one is lower than expected. So in that case, we can say that the distribution can be clustered, right? But we don't know that. We have to run the z-score, to look at the p-value, if the p-value is significant or not, right? So that's why the z-score is calculated to see whether the results are statistically significant or not. And here also mentions that if the index is less than 1, the pattern can be clustered, right? If it's greater than 1, which means that the observed is more dispersed compared to the expected, right? But you also have to use the z-score to see whether the results are statistically significant or not. So in ArcGIS Pro, here, average nearest neighbor, and so your input feature class is going to be the desk, so I'm going to find the average nearest neighbor for desk, right? And it's here. So generate report and area. So if you don't select the area, area is going to be the minimum enclosing rectangle, right? So if what is the minimum rectangle that I can have based on all of these points, right? So I select this, I do not change this, the default is okay, and then run. All right, so now if you click on view detail, so the observed mean distance is 10.5, right? But the expected is 14.2, right? So the observed is lower than expected, so it's obvious that the ANN is less than 1, which means that it's more close to each other, more clustered, right? But we still don't know that. So as you can see, the ratio is 0.74, is less than 1, so it kind of implies clustered. But still, we have to look at the p-value, the z-score. So the z-score is very large. So the absolute value of the z-score is very large, and then, so which means that the p-value is very small. The probability that the distribution is random is very, very small. So we reject the null hypothesis that the distribution is completely spatial random, and the distribution can be say that it's clustered. So if you also click on this HTML file, so the p-value, the z-score, and also it shows that it's a totally clustered distribution. All right, so that's how you can evaluate the existing pattern from a statistical viewpoint using average nearest neighbor. Again, there are multiple ways you can analyze the distribution of the point pattern, but the simplest one, average nearest neighbor. But how about, so these techniques, as I already mentioned, like for the previous labs, that using global Moran's I or general G, so these are global measures, okay? So they just tell you that whether the distribution, is there any clustering, yes or no, right? But they cannot identify the location of the clusters, right? So how can I find the location of the cluster? Is there any hot spot? Is there any cold spot of the desk or not, right? So in order to do that, what I'm going to do is I am going to create a grid, and then for the grid count, so it's going to be a polygon feature, right? And then for the grid, I'm going to count number of the desks that are within each of these cells of this grid, right? And then after I count it, I can run the GEDIS or local indicator spatial autocorrelation, or LISA, to identify the location of the hotspots of the desks in this study area. So first of all, let's create a grid. So tools, and then I type grid, and I am gonna select, and here I'm gonna select generate grids and hexagon. So I am going to first of all create a grid. So let me remove this. Where is the area that I'm going to create a grid? So I'm going to use the AOI, area of interest, which was the 3 standard deviation ellipse, right? So this is AOI. So the output, I'm gonna just call this grid, grid, right? And so you can have the grid in different shape. You can have it as a square, you can have it as a hexagon, and H3 hexagon or more advanced hexagon. So I'm gonna just use the hexagon. And so here is very important. So what is the cell size of the hexagon? So the default is 1 mile, which is too much, right? As you saw, this very the distances are based on meter, and they're not too far from each other. So you can, for example, use the grids that are 20 meters and 20 meters, right? So it's going to be 400 square meter if you want to use, for example, the square. So I'm going to use another value, like for example, 500 square meter based on the hexagon, right? So I'm going to, for example, use this value, which is kind of close to 20 by 20. So if I use this 500 square meters, so each side is going to be almost 14, 15 meter, okay, if I use the 500 square meters, right? So you could also use 400 square meters for the, I don't know, for example, the not hexagon, just use a square. And then run. So what happens is that it creates a hexagon, as you can see. So the size are okay, and it is within the area of interest. So the next thing that I'm gonna do, I'm going to count the number of the points that are within this, each of these cells, right? Each of this hexagon. So the tool that I'm gonna use to count, if you want to count number of points in the polygon, the most basic tool that we can use is called spatial join. So we join these points to the this grid, right? So I'm gonna type spatial join, and so my target feature is going to be this grid. So I'm gonna join everything, these points to this grid. So the target feature is going to be this grid. So the join feature, I'm going to join what to this grid? I'm going to join this, right? So the join feature is going to be this. Okay? Join 1 to 1, and everything is good. So intersect is also okay. So if they intersect, it will be joined, and then run. So what happens is that it created a new feature class, spatial join. If you open up the attribute table, it created another field, join count, right? So for example, here we have 9. So let's see if it's true or not. So if I select this, there should be 9 points in this field. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or here also is 9, right? 2, 4, 2, 4, and also 9. So if it intersects, it calculates, it considers that. And for example, let's say here 4, right? So it counts number of points within each polygon, right? So now I can, so instead of this color, I'm gonna create, for example, a graduate color, right? Based on joint count. So here you can see the count of deaths in each of these cells, right? And now that I have the data at the polygon level, I can easily run the GEDIS or GIS star or local Moranzai. So if you go to the Analysis tab, Tools, Mapping Cluster, GEDIS or GIS star. So my input feature is going to be a spatial join, right? So the input field is going to be based on the count, right? Joint count. So I want to see if it has a cluster distribution or not. So here is the spatial join hotspot. And so how can I define the neighborhood? I'm going to define the neighborhood in this case based on the distance. So the closer you are, the higher importance, the higher the values are. So I'm going to use the inverse distance here, and then run. Okay, so here are the location of the hotspots. As you can see, most of the hotspots with 99%, 95% confidence level are very close to the Broad Street pump. So from statistical viewpoint, I am 95%. There's a hotspot here, there's a hotspot here. So as you can see, they are very close to the Broad Street point.